Hey, good afternoon, everybody. Welcome to our second IFISC colloquium, and it's a particular pleasure to introduce our speaker of today, Professor Eckehard Schöll from the TU Berlin. Some of you might have already met him. 3 weeks ago, we had organized a conference here in Saint-Malo on delay coupled systems, which has been a great success and also a great pleasure organizing it with Eckehard here. And it's not only that organization of the conference, we are connected already for several years in a very fruitful and, as I find, very enjoyable collaboration. But there are others here in the room who know Professor Schöll a lot longer, and I will not say years, but Professor Schöll and Maxi already met many years ago in these previous, is it summer schools or?
It was, at that time it was summer school.
In Sistemas, which have been very famous and still are ongoing. There's certainly a lot to say about his CV, and you see I need even some extended memory, otherwise I would forget important things to say about him. And still, I only can give a very brief version of his CV. Professor Schöll studied physics in Tübingen in Germany and got his diploma in physics from there. Then he made a step towards the UK, to Southampton, and got his PhD not in physics, but in applied mathematics. But then he thought, well, that's probably a bit incomplete. He should get a PhD in physics as well, and so he did at the university in Aachen. And then he stayed also for several years in Aachen, where he got his Wiener Legendi and became already the first professor position there. Got the first professor position there, and then moved in 1989 to where he's still at the moment, to the Technical University in Berlin, being a professor for theoretical physics there. He has, in the meanwhile, had many different research days or visiting professorships at different places like Wayne State University in Detroit, University of Florida, Duke University, a grant of the Royal Society of London, Mathematical Society, Royal Mathematical Society? Mathematical Society. I thought in UK everything's royal. So he has been working on many different topics. Actually, in the beginning, he was already very close to what we're doing here, working a lot on semiconductor lasers in collaboration with different people like Dieter Wimberg, who's also meanwhile at the Technical University in Berlin, doing works on gain switching, pulsations in lasers, but also at a very early stage already works related to chaos in the mid-80s, something like that. But he has been working in many other fields like quantum transport, in quantum well structures, self-organized growth of growth mechanisms in materials. And fortunately, after he had moved away for a long time from semiconductor lasers, he came back to that field, I think it's about 8 years or something ago. And since then, we benefit a lot from this fruitful collaboration. But besides that, he's also been working, so if you think of nonlinear dynamics, all the general aspects from pattern formation, chaos, noise, a lot on control. And that applies then to laser systems, neural systems, and transport in nanostructures. He is also, he has published many books and publications on that. I think meanwhile it's more than 400 papers. And he is very well known, not only for organizing the meeting that we had a few weeks ago, but he is or has been the organizer of what is meanwhile the biggest physics conference in Europe, right, of the German Physical Society, the spring meeting, and he has been twice already hosting it at the Technical University in Berlin. Some of you have been there this year, and this is a conference with almost 6,000.
Almost 6,000.
This time over 6,200 participants. So for those who have been there, know what kind of a huge meeting that is. What is also worth mentioning, he is the speaker of this very prestigious collaborative research centers in Germany, and he is the chairman of the one on control of self-organizing nonlinear systems, which has just started last year. End of last year, right? Beginning of last year. Okay, and has already been the vice speaker of two previous collaborative research. Some of you might know them. One was 12 years running program 1998 to 2010 on complex nonlinear processes, where we also had a lot of connecting points. So today he's going to, I don't need the extended memory, you see the topic. He will provide us an overview on adaptive control and synchronization in delay coupled complex networks. It's a particular pleasure having you here, and the floor is yours.
Thank you very much, Ingo, for your kind introduction and for the... So, thank you very much, Ingo, for the kind introduction and the invitation. It's a great honor for me to be here and give the second colloquium at IFISC. And it's also a great pleasure to be in the Institute and interact with many of you. The talk I will give focuses on adaptive control and synchronization in delay-coupled complex networks. This is work done at the TU Berlin in the new Collaborative Research Center on control of self-organizing nonlinear systems, which was just mentioned by Ingo. And it is in collaboration with many people, but in particular the subjects I'm touching today have been in collaboration with Alexander Fratkov and Alexander Selivanov from St. Petersburg State University and Russian Academy of Sciences, and Judith Lehner Thomas Dahms from TU, Philipp Höbel from Northeastern University, US, and Valentin Flunkert, who is now here at IFISC with Ingo, and Sergei Janchuk from Humboldt University. So I will give you an outline of, first of all, what is delay, why is it interesting, in particular in networks. Then I will give some formal framework of classification of delay-coupled networks for large time delay, focusing on the stability of synchronization. I will briefly dwell on applications to neural networks and to coupled lasers, and then I will come to cluster synchronization, controlling synchrony in a more general sense, and finally I will talk the new subject of adaptive control. So delay is ubiquitous in nonlinear systems. You find it, for example, in mechanical systems when you deal with the problem of balancing a stick, or the Segway, the famous Segway is just a pendulum which is standing upright and you have to somehow control it to balance it. And there is delay involved. Electronic systems, whenever you have capacitive effects or latency due to signal processing. Optical systems, this is of course well known to most of you. The signal transmission time gives rise to delays, and this is important for many devices like lasers coupled to external cavities or just to mirror with feedback, or optical injection and optically coupled lasers. Also, there is great interest in delay in biological systems. The cell cycle time or biological clocks involve some delay, and in particular neural networks, there's always delay in the coupling and also possibly delayed feedback. So, as a mathematician or a theoretical physicist, why is delay interesting in dynamics? Well, even if you consider the simplest ordinary differential equation, linear ordinary differential equation here, if you add a delay term with some delay time tau, x of t minus tau, it already generates a lot of interesting complex dynamics, and the reason is that this delay extends the phase space of the system to infinity. It introduces infinitely many eigenmodes, countable number of eigenmodes. And so simple equations can produce very complex behavior. I'm very much in favor of simple equations because you learn a lot and get insight about mechanisms if you study simple equations, and still you can generate very complex behavior like delay-induced bifurcations, delay-induced multistability, or on the contrary, you can stabilize unstable periodic states or stationary states. So now I'm coming to the second keyword, complex systems or complex networks. Well, they arise everywhere in the brain, for example, where you have neurons which are coupled to other neurons via the synapses, and also there's some coupling with the blood vessels, cardiovascular coupling, and so on. Technological networks like the internet or the web, the World Wide Web, or even the power grids. Here you have a picture of, which reflects the lighting, which is a reflection of the power grid, and in the United States, and here you see this dark spot, and it is was in fact taken in 2003 when a large portion of this power grid failed on the eastern coast. This was a quite tremendous effect, and of course it is important to understand the dynamics of networks like these power grids in order to avoid such failures, such cascading failures of the network. Quite different fields, sociology, economics. Here is a network of friendships. These are data taken from a US school, and you see there are yellow children, there are green children, and there are red children, and there is some sort of assortativity. You see some of them mix within themselves. And so it's a rather complex network composed of individuals. And the links are given by their friendships. So synchronization in networks is of general interest. And sometimes synchronization is wanted, sometimes it's not, sometimes you want to desynchronize. For example, the constructive role of synchronization for strongly coherent fields. In lasers, you often want to synchronize them for communication purposes and so on. On occasion, however, it's also undesirable to have a synchronized state. For example, there are pathological states, neural states in the brain, where the neurons all fire synchronously, and this can lead to disease like Parkinson's tremor or epilepsy, and here you want to avoid it. Or if you think of the London Millennium Bridge, which just a few days after it was opened, showed quite strong oscillations, which were not expected when a lot of people walked on this bridge. Of course, you would expect such resonance if they walk all in one step, but they just walked on the bridge randomly, and this you can model this, and this was in fact modeled by several people, Stroger and Eckehard and others, by a very simple model which very accurately described what happened. As soon as the number of people walking on the bridge exceeded a certain threshold, transition set in, which gave rise to this lateral swaying motion. So this is a synchronization of the people which spontaneously happened when they were walking due to their interaction with the bridge, and this is also a network. So this is what you want to avoid. Now, there are mathematical tools to study the stability of synchronous solutions, and a very powerful tool is the multistability function, which was proposed by Pecora and Carroll for complex networks of this form. Here you have a variable xi, which has a local dynamics, nonlinear local function f of xi, and some coupling with the coupling matrix gij to all the other variables with some coupling function h and coupling strength sigma. Now, this complex high-dimensional problem can be broken down by an ingenious method which is called the multistability function. It basically consists in splitting the problem into a topological part where only the eigenvalues of this coupling matrix matter, and a local dynamics part. This is just the linearized form of the local dynamics. It does not involve, it's not the full dimension n of the complex coupled network, but it's just the local dynamics with some parameter, some complex parameter alpha plus e beta, which takes care of this coupling. And these are the Jacobi matrices. Now, it's sufficient to study the maximum Lyapunov exponent of this local dynamical system as a function of the complex parameter alpha plus I beta, and then check whether this Lyapunov exponent is always negative. If you plug in the eigenvalues of this matrix, or whether there's one eigenvalue for which is positive, and then it's unstable. In the other case, it's stable. So it's basically a method of diagonalizing this problem. This was originally introduced for systems without delay. Now we are coming to networks which involve some delayed coupling. And this is an interesting question now. How does synchronization and delay interact with each other? There are important examples, for example, synchronization of neurons in the brain, I've already mentioned it, and chaos synchronization of lasers, which is a promising method of encrypted communication. And so in all these networks, in all realistic networks, delay plays a role. This topic has become a quite important and vivid subject for a number of years, and I just want to point out one seminal paper here, which is due to Ingo Fischer, Claudio Rasso, and other people involved here, which opened a whole new door to this field. And successively, many papers, many works dealt with these delay-coupled networks, experimentally, theoretically, applications. I would like to point out that the multistability function can be extended to these delayed systems just by writing the coupling term in this form, where we have the delayed variable xj, delayed by tau, minus the non-delayed part. This is often a form which is used in neural systems when you have some diffusive-like coupling, but you can also skip that term, and that's the form which is used, for example, in laser dynamics, in Kobayashi laser dynamics. Both can be treated in the same footing. And I want to point out again some early papers by Yirsar, by the group of Otti, Dos, Dankert, Ingo Fischer, and also the Kienzl and Ido Kanter groups. And we also did some work on that. But there are many, many more papers which I unfortunately cannot mention here. There have been conferences on that. It has already been mentioned by Ingo just 3 weeks ago here at the IFISC. There was a conference on delayed complex systems, and which some of you, I guess, attended. And there has been a theme issue on delayed complex systems published 2 years ago, following another conference on delayed complex systems held at Max Planck Institute in Dresden. So I think there's currently a lot of interest in this topic. So let me come to the first technical part, in which I will point out some universalities which allow one to classify the synchronization behavior in general systems, general delay coupled networks. And the approach is based on the master stability function. Here I've written the dynamic equations in the form of a map, iterated maps to make it easier, but the same can be done for flows, for continuous flows. Again, the local dynamics and the coupling function. Now the important parameters are the eigenvalues of this coupling matrix. In fact, one eigenvalue is given by the row sum of the coupling matrix. This is a constant. This is necessary in order to obtain synchronization, because every node needs to get the same input, otherwise you cannot get a synchronized state. And this is reflected in the fact that this row sum is constant, and it is also an eigenvalue corresponding to the motion in the synchronous manifold. So with the eigenvector 1, 1, 1, 1, eigenvalue sigma, you describe synchronous motion. The other n-1 eigenvalues of the coupling matrix are transverse eigenvalues, and they describe the deviation from the synchronization manifold.
Just a simple question. A typical value for n, capital N.
Yes?
How large would be n in typical manner?
Any number. Well, one starts with networks, with simple network motifs,
Yes.
which have n equal 2, 3, 4, 5. There you can get some insight. But then typically, if you talk about lasers or, well, maybe several tens, up to 100, and if you talk about neurons, 10 billion neurons, but that's beyond simulation, and I think it's not necessary to simulate it, because you can already get enough insight by simulating several hundred nodes. So that's what we usually do. We simulate several hundred nodes.
Several hundred.
Yeah. Okay, so the analysis of the stability proceeds in the usual way by looking at small perturbations around the synchronized solution, perturbation psi, Ti, and then linearize the equation and diagonalize. And you get a set of variational equations of this form, which I already showed in the transparency of the master stability approach, where now this parameter here, the parameter in the coupling term, is given by the longitudinal eigenvalue and the transverse eigenvalues of this matrix. This is actually the approach which Valentin took in his PhD thesis, and he obtained very interesting results, general results for large delay. Now, first of all, it's quite obvious if this complex parameter here describes the eigenvalues of the coupling matrix. Well, for the moment, we will just leave it as a parameter and discuss what happens with the Lyapunov, with the largest Lyapunov exponent, lambda max, as a function of this parameter. This is called the master stability function, the largest Lyapunov exponent as a function of this parameter. And if you plug in the longitudinal eigenvalue, the row sum, which describes synchronous motion, if the Lyapunov exponent is greater than 0, the system is chaotic. If it's less than 0, it's not chaotic. However, if you plug in the transverse eigenvalues of the coupling matrix, this describes how the motion away from the synchronization manifold behaves. So this describes stability of the synchronization, if it's negative, or instability, if it's positive. So the basic plot is this master stability function as a function of the real and the imaginary part of this complex parameter, and the positive colors, well, the brownish colors denote unstable synchronization, and the white and grayish colors denote stable synchronization. So it now just depends whether your transverse eigenvalues are located inside this white gray area, then you have stable synchronization, and also you can decide, or you can determine whether the motion in the synchronization manifold is chaotic or not chaotic, depending upon the position of this eigenvalue sigma. So the first observation of Valentin was that for large delay, the maximum Lyapunov function as a function of this parameter does not depend upon the angle, but only on the modulus. So it's rotational symmetry. You have this rotational symmetry, and this can be shown quite generally. For large tau, it's related to the spectrum. of the delay equation. And now we have either the situation that at the origin the Lyapunov exponent is negative, and then it's monotonically increasing with r, and at some radius it becomes positive, so unstable. Or it's positive right at the origin, and then it remains constant and unstable everywhere. So the example which is shown here is the example of the Milan-Kobayashi equation, which describes coupled semiconductor lasers, and I'll come back to that later. And you see for different values of the time delay increasing from red via blue, via green to gray, it becomes more and more rotationally symmetric. In fact, already at that point, I think you cannot tell with your bare eyes whether there are deviations from the rotational symmetry. So the approximation that it's large, delay must be large to get rotational symmetry works rather well already if you have, let's say, 2 or 3 times the intrinsic timescale. The intrinsic timescale of the Milan-Kobayashi equation here. Okay.
Sorry, because this parameter R is the strength of the coupling?
And the parameter, the complex parameter R e to the I psi, you have to plug in the eigenvalues of the coupling matrix. Now, if you have unidirectional coupling, for example, then they are complex. They are complex quantities. And the bidirectional ring has a real parameter, so in that case, the phase is always 0 and you're always on this real axis. Does that answer your question?
No, actually, I mean, I was trying to interpret this in simpler terms in terms
Okay.
of
I think
how can I read the, I mean, so an important parameter is how strong the oscillators or
it's the
nodes
topology
are.
of the coupling. The topology, it's only exclusively the topology of the network which determines its eigenvalues. So, for example, for a ring, you get eigenvalues located on the unit circle. And for star topologies or for random topologies, you get other distributions of the eigenvalues. So this is a purely topological measure, where this lambda max is a dynamic measure. It's the largest Lyapunov exponent. So I think conceptually one has to keep clear of these two. Although both are eigenvalues, well, in some sense. So now we can classify networks in these 3 classes according to the relative size, well, in terms of the modulus, of the maximum transverse eigenvalue of the coupling matrix and the longitudinal one, the rho sum. And because previously we've seen that if the Lyapunov exponent at sigma is greater than 0, we have chaotic dynamics. It is in fact greater than 0 above that critical radius. So now it depends upon whether the transverse eigenvalues are also greater than this radius or not, and that determines whether the synchronization is stable. The chaotic synchronization is stable. Well, if the equal sign holds as well. But if the greater sign holds here, so if the maximum transverse Lyapunov exponents are larger in modulus than the longitudinal one already has a positive Lyapunov exponent because chaos, so then synchronization is unstable. So in these cases, always the synchronization, the chaotic synchronization is unstable. In that case, it depends upon the radius, and one can get some more detailed results. This has been done work by Heidenthal and Thomas Dahms in collaboration with the groups Wolfgang Kienzler and Ido Kanter. For non-chaotic synchronized dynamics, the longitudinal eigenvalue is less than the critical radius, and therefore synchronization is always stable. Periodic synchronization is always stable. And in that case, class C, it again depends on the value of the critical radius related to the maximum transverse eigenvalue. So let me give some illustration, some examples. The topology determines the eigenvalues, and therefore one can conclude that rings of unidirectionally coupled elements are always unstable with respect to chaos synchronization. So no chaos synchronization is possible in these topologies. This is a topological property which actually was already noted in a special case, in the case of zero row sum by Wolfgang Kinzel, and this gives the general result. By the way, this has been applied, these network motifs of few elements have also been applied to lasers, including the role of phase in a recent paper by Valentin Flunkert. I think he has already talked in this institute about it.
You are not including at all the dynamics of the elements.
The dynamics of
the elements, of the nodes.
It doesn't depend upon the dynamics of the
but
nodes.
you know that if you have, let's say, two neurons excitatory inhibitory, I think that zero lag is stable, not unstable. So in that case,
with delay, with large delay,
with delay.
The result is only valid for large delay. For large delay, it's always unstable.
I see.
So another class where chaos synchronization is possible, but non-chaotic synchronization is always stable, is given if you add this self-feedback loop. So it's just the motif before, with two lasers or two nodes, and you add this. So this is well known from the laser example, from Uwe Fischer, for example. And then you get stable. You can get stable chaotic synchronization, and all rings with bidirectional coupling or mean field, or to all coupled systems, or systems with only inhibitory or only excitatory coupling also fall in this class. Now, let me illustrate this by some examples from neural networks. And the first example is the Fitsunagumo model, which is a generic model for excitable systems for neuronal activity with two variables, activator and inhibitor. And the activator dynamics has this nonlinear local dynamics with the coupling to the inhibitor. And the system, now if we have one node described by such dynamics, we can couple this to other neurons with this diffusion-like difference coupling. This can also include self-coupling, of course, and the coupling function here is just a simple matrix where the activator is coupled to the activator. In terms of the phase portrait of the local dynamics, the activator and the inhibitor, the activator and inhibitor variables, the null isoplines look like this. So you have a stable fixed point here, which is just below the threshold where it becomes unstable with respect to Hopf bifurcation. If you move this green line further on into this regime, it becomes unstable, but we are still in the stable regime. However, this is an excitable system, so if you keep the system a little bit above that threshold, it emits a pulse of this shape. This is the activator pulse. If you couple two such systems with delay, the systems receive mutual inputs from each other after some delay, and that induces periodic spiking. So only in the coupled system you observe periodic spiking, and the time delay sets the period. If you do the analysis for this system, this is the master stability function. It's rotational symmetric. In fact, here it already is rotational symmetric for rather small tau. So the asymptotic limit for large tau is already satisfied quite well for much smaller tau. And the stable regime is the one where the maximum Lyapunov exponent is negative, so the bluish, greenish color here. And now the topological ingredients are the eigenvalues of the coupling matrix. Since this is a bidirectionally coupled ring, they are real and they are located right here. The one is always at 1 real, this is corresponding to the row sum, to the longitudinal motion, and the others are also stable because they're inside. So we have stable, synchronous, zero-leg motion in the system as long as we have only one type of neurons, excitatory, for example. Excitatory. And as already was mentioned, if we mix excitatory and inhibitory neurons, now let's do this and introduce a few inhibitory links. Add randomly Well, we start with a regular network of excitatory neurons. These couplings which are shown in green are excitatory, so they are nearest neighbors and next nearest neighbors coupling. In fact, we can have R range, K is equal to 2 if we have next nearest, or K equals 3 if we have next nearest, and so on. Now add in a random way some inhibitory links. This is similar to the Newman-Watts procedure for small worlds. It's not exactly a small world but it adds some inhibitory links. And now these are just two realizations with the same probability of adding inhibitory links. And you can see the master stability function here and here is of course the same, but the eigenvalues are different. And here all the all the transverse eigenvalues of the coupling matrix are in the stable regime, so stable synchronization. Here one is slightly outside, this one, so we have desynchronization. If you take an ensemble of randomly generated networks like this with the same probability p, some of them will synchronize, some of them will not. And if you plot the fraction of those which are desynchronized as a function of this probability of adding inhibitory links for a certain k, let's choose k equals 18. This is this blue curve here. And for the other ranges of coupling, it just looks the same, just shifted. But let's look at that one. Then they are all synchronized up to a certain threshold probability of introducing inhibitory links, and then they are strongly desynchronized. This goes to 1. Of course, this behavior reminds one of a phase transition, and in fact, if you have a finite system with 40 nodes, it's still not a phase transition, it's smooth. But if you increase n, 60, 100, 200, 500, 1000, then you see that it becomes very sharp, and eventually in the thermodynamic limit sharpens up to a discontinuous transition. This was my example for neural systems, and now I'd like to add an example with laser networks. The simplest laser model with delay due to the signal propagation between different lasers is this, and this local dynamics here is the Kobayashi model, where we have the inversion n. This is all dimensionless, so carrier inversion dimensionless. And we have the electric field, which is a complex parameter, so we have split it into real and imaginary parts. And T is the time scale ratio of electrons and photons, and alpha is the line width enhancement factor, phase amplitude coupling. The coupling here is between lasers is through the optical field, so this is the 1-1 coupling matrix. And this is of interest, of course, for many reasons. Chaotic dynamics can be used as information carrier, secure communication builds on that, and also the Kobayashi model is a paradigmatic model in nonlinear dynamics. So, what happens if we look at, for example, a system of 25 lasers? This is just an example with a random network, that is a random network with a probability of wiring two links 0.8, and this is the delay time used, and you see that the system behaves chaotically, but it's synchronous, so it's chaotic synchronization. All these nodes flash synchronously, but in a chaotic way. So this is in line with the results of the master stability approach. And if we look at the master stability function as a function of this probability of linking two nodes, P. The master stability function is rotational symmetric. We have the green regime which is stable and the orange-yellow which is unstable. The eigenvalues of the coupling matrix are these blue dots. And you see there are many of these because it's a high dimensional. Well, it's n equals 25. So there are 24 transverse eigenvalues of the coupling matrix and one longitudinal one, which is outside the stable regime because it's chaotic. So this one's chaotic synchronization. And clearly this is stable synchronized behavior. 0.8. Now what happens if we decrease the wiring probability between two nodes, the eigenvalues ensemble changes. In fact, it spreads out 0.6, 0.4, and here already some of them get outside the stable regime, and here many of them are outside. So if you decrease the wiring probability between two nodes, it's a more sparse network of lasers, then synchronization becomes unstable. Okay, now I'm really running into trouble with time because I really want to tell you still a little bit about adaptive control, and before I can get to adaptive control I have to introduce the Stewart-Landau oscillator model. But I think this is probably known to many of you because it's a generic expansion of a nonlinear system close to Hopf bifurcation. Let's say a supercritical Hopf bifurcation. Then in complex variables z is a complex number. The local dynamics is just the bifurcation parameter, the frequency. Here we have some parameter of the third order term with some chirp, gamma, amplitude phase coupling. And so this describes the Hopf bifurcation as lambda tends to 0. We are in a regime where we have oscillations, periodic oscillations of the local dynamics. And now we add the coupling strength, coupling matrix, the delayed difference, other nodes to the node J. And the important point is that here we have a complex coupling constant. Sigma is the real K times e to the I beta with some coupling phase. The coupling phase, in fact, is important if we are talking about cluster synchronization, because it will, in fact, determine which cluster synchronized state is stable. And the constant rho is some condition, as always. Now, I'm trying to be not too technical now because I'm short of time, and so I'll just explain the main steps of the theory. In fact, we are looking for a collective amplitude, R0, which is the same for all nodes, and the phase of the different nodes for zero lag synchronization is just a collective frequency times t. This is zero lag synchronization or in-phase synchronization, where this m, this parameter m is 0, so this term is absent. However, we can have cluster states, or where several nodes have the same phase, but there's a phase difference. Here we have 3 clusters, we can have more clusters. In fact, if we have n nodes, we can have n clusters, and that's called the splay state. So by this parameter, little m, we can decide whether we describe the zero lag in-phase synchronized state or splay or cluster state. And it just, this parameter m just determines the phase difference between subsequent neighboring nodes. So I think this is all we have to remember for the moment. One can do the stability analysis, apply the master stability function, and the nice thing about this Stewart-Landau system is that you can do everything analytically, because the Jacobian, the linearization matrix, does not depend upon time, even for the periodic state. So you, instead of involving complicated Floquet theory, you can just calculate the eigenvalues of the Jacobian matrix. And this can be done. And then you end up with a condition for the characteristic equation of these eigenvalues. So the dominant Floquet exponent is given by this capital lambda. And as always in these delay systems, this is an implicit equation because the delay term introduces terms of the form e to the minus lambda tau. So you cannot just simply say lambda is equal to minus k as for the non-delayed system, but you have to solve this complex equation, and sometimes you can solve it by the Lambert function, sometimes you have to do it numerically. But in this case, fortunately, one can get really analytical results on the stability involving theorems from theory of matrices, like Schrolling's theorem, which tells us where the eigenvalues of the matrix are located in circles. And so, as a final result, we find that for certain coupling phases, beta was the phase of the coupling zone, we can stabilize the different cluster states, either the in-phase state for that choice, or the splay state, or the cluster state. So this is the result for a network of 4 nodes with coupling phase 0. We have high multistability. The different colors denote all different multiple stable states. For example, the yellow one here we have just the splay state and this in-phase synchronization state, but all the other colors are associated with multistability of different of these states. In-phase play cluster. So with the coupling phase 0, we have multistability. However, if we tune the coupling phase to those values which I mentioned just in the previous slide, omega tau, the collective frequency, or minus pi half, or minus pi, or minus 3 pi half, we can lift that multistability, and the zero lag state is always stable in the whole parameter plane, tau k. Here, or the cluster state is always stable, always play stable. Now, let me illustrate this by a simulation. And I'm going to show you a simulation of the Stewart-Landau oscillator, which oscillates, well, on this asymptotically oscillates with a common amplitude. Here in the in-phase state, all the nodes coincide. Here the play state, here the cluster state. So let's look at this. First of all, with no coupling, well, all individual oscillators somehow move and obtain a final state. This is the unit circle, but they do not interact. Now, let's put the coupling on. This is, by the way, a simulation with slightly non-identical frequency. So there's a frequency distribution with some variance, which is relatively small, but still non-identical. But with beta equals 0, the theory for identical oscillator predicts that we have high multistability, and in fact we get a state depending upon the initial condition. In that case, it is a play state. However, if we choose beta equal to one of the following values, either the omega tau or omega tau minus 1/2 pi over n, or 2 times 2 pi over n, or 3 to 2 pi over n, we successively get different cluster states. We stabilize different cluster states. Here you see that we have stabilized the in-phase state. Now, changing beta to the next value, you will see after a while of asymptotic behavior, this beautiful flower comes up, and this is the order parameter, by the way. The order parameter which is plotted is the red dot. And now we have this play state. And again, changing beta takes a while before these interact. And we have the 6th cluster state asymptotically. And changing beta. Now you see the 4-fold symmetry comes up, so eventually we have a 4-cluster state, and so on. So we can already you can realize all those according to what was predicted. Now let me stop this and go to the last part for the last few minutes, because this is now where adaptive control comes in. Now, the analytical result, of course, only works for the Stewart-Landau because we are fortunate with that dynamics. And also it only works for very special values of beta. It would be nice to find the coupling phase by an adaptive algorithm. And this is in fact provided by the speed gradient method, which is a well-known optimization method in control theory. So what one does is one defines a goal function Q, which is typically convex and has a minimum at the final state which you want to realize. So the speed gradient method tells you to tune the control variable U in such a way that you always follow the steepest descent, not of this function Q, but of the speed. The Q dot is the speed. Why the speed, and why not the simple gradient method of optimal theory? Because if you define a simple goal function, it will generally not depend upon the control parameter which is in the coupling. So if we use the speed gradient method, which means go along the trajectory, then the dynamics comes in, the dynamics x dot, and in the dynamic equation, the local dynamics, we have this parameter u. So this means in the special case where the coupling phase is the control variable, that we get a dynamic equation for this coupling phase. Gamma is the relaxation constant. This is the speed, the gradient of the speed, the cost function of the goal function, and you can plug that all in, and then you can solve it and simulate it. And the question is, what should we use as a goal function. Of course, this is not unique. You can use any convex function which has a minimum at the desired state. And here are two possible choices. One is a simple quadratic. This is probably the one would think first. However, it has a drawback because it does not reflect the 2π periodicity of the angle. So it does only work if the difference between two phases is less than 2π. You can also use this one, which is based on the Kuramoto order parameter. This is in fact 1 over n times the sum over these factors is the Kuramoto order parameter. So it becomes 1 in the synchronized state and 0 in the desynchronized state. If you take the modulus of the Kuramoto parameter, which means this one times the complex conjugate, and subtract it from 1, this has a 0 at the desired 0-leg synchronization state. Before I show you the results, I would like to arouse your interest or your motivation why this could be possibly of interest. Well, this method of self-adaptively finding the control parameter such that a certain desired synchronous state or a certain state in general is achieved could, for example, find the optimum control strength for stabilization if the parameters are drifting, if the system parameters are not known, or if they are slightly drifting. And so what I've done here is, or what we've done here, this is work done by Willy Lehnert, Philipp Höhl, and in collaboration with Alexander Fradkov and Peter Usenko. We have defined a simple quadratic cost function for the simplest system we can think of. This is the system complex variable z, lambda plus I omega z. It has an unstable fixed point, an unstable steady state in the origin, and we want to stabilize this by time delayed feedback control. So what we have done is we plug in the speed gradient algorithm. Well, first of all, in the simple case, of course, we can also analytically calculate the regime of stability where the fixed point is stabilized. If it's unstable without, if lambda is positive, it's unstable without control. Now if we add feedback control, the Dirac type, we get this green area where stabilization of the fixed point is achieved as a function of lambda. And starting with lambda equals 0, we slightly increase lambda. This is done with a function externally, so this simulates the drifting parameter. It's increased and then decreased again. So if we are initially here, let's say, and increase lambda, the state becomes unstable, and the adaptive algorithm now self-adaptively finds a new value of the control parameter k to achieve stabilization again. So we go here. Then it's still stable if we increase lambda up to this point, it becomes unstable, and then the algorithm again adjusts it. So it continuously adjusts the control parameter, always to stay in the stable regime, and then if we decrease lambda, there is no need to further adjustment, so it just remains. So this is actually capable of helping with drifting parameters. And now I want to show you the simulation for the network, for the more complex system. And what we've done here is first of all, we've taken the simple goal function for an Erdős-Rényi random network with 6 nodes. And the radius of the radii of the individual nodes are shown here as a function of time, and you see that they converge, so it's a collective radius, and the phase difference is here 1, 2, 3, 4, 5 between the 6 nodes are equal to 0, and the coupling phase adjusts itself in this way, and finally obtains a value which is close to the one which is given by the master stability function, by the analytical result previously here. But this analytical result, as I told you, only holds for specific values, and we cannot get any results if we deviate. Probably there's a whole range of values for this holds, and the algorithm finds one, and the goal function goes to 0. Now this would be nice if we can apply this also to cluster synchronization, and this is in fact possible, but it is a little bit more involved. And I think how much time do I have? Okay, so then I'll skip this. Let me just tell you that you have to think a little bit more carefully if you define the cost function for cluster synchronization, because what might happen is that if you have a 0 for a certain well, this is the generalized order parameter, then you could also all the divisors of the desired cluster satisfy the zero. So you have multistability and you want to suppress those by imposing a penalty. So basically you put in additional penalty term. This is this one. And then it again works, and you can stabilize the display state, or the two cluster state, or the three cluster state, or the phases converge here. So yes, let me come to the final few transparencies. This is also robust with respect to distribution of the parameters of these individual nodes. For example, the frequency and the damping rate of the individual nodes, if they deviate, well, we use the Gaussian with a 1% standard deviation. This basically looks the same as before. The phases converge for the three cluster state here, for the, and the goal function goes to 0. If we make the distribution too wide, then synchronization does not work anymore. So it becomes worse. Well, it's still somehow synchronized, but the phases are not exactly identical. And if we further increase it, we will not get synchronization. That's what we can expect. Also, one can simultaneously control all control parameters, the strength, the phase, and the delay time. This also works. Takes a little bit longer, but it works. And finally, and this is my final point I want to make, one can use this adaptive, self-adaptive algorithm to adjust the network topology. This is very recent work, and we start from the previous goal function, but now we have to add a term which guarantees that the constant row sum condition is preserved. Otherwise, we cannot get synchronization. And now we adjust the link probability, Gij. So the matrix, the coupling matrix, is the control parameter which we want to adjust. And in fact, this is a simulation for, I think it's a simulation for a few nodes which are originally in the initial condition is set such in a unidirectional ring that the 4 cluster synchronization is stable. These are 12 nodes, 4 cluster is stable, so we get 1, 2, 3, 4 different phases. At that point where this line comes in, the adaptive control of the coupling matrix is set on, and then this coupling matrix is adjusted, so links are generated. Initially we have only links with probability 1 on the unidirectional ring, and we have all other 0, and now a lot of other links come on. This is a rather weird picture, so let's look at the network topology, which gives you a better impression. This is the ring with which we study, with which we start, which has as a stable solution only the 4 cluster state and not the 0 lag state. And we want to adjust the couplings such that the 0 lag state becomes stable. And after some time, links are formed. In fact, here the blue ones are excitatory and the red ones are inhibitory. And some more links are formed, and the strength is the thickness of these links. And finally, all the nodes have the same phase, the same color means the same phase, and also a lot of new links are introduced. Well, I'll leave this as a puzzle for you. If you want to ask me in the discussion, I will explain why the eigenvalues of the master stability function are still outside the regime, although they are a little bit compressed, but it seems, well, it apparently seems to contradict the master stability function, but it does not, I can tell you. And this is my final slide, which is a 30-node model, and we are stabilizing the 6 cluster synchronous state. If you noted, we start with a unidirectional ring, and now, well, the nodes are moved to make it clearer what happens. What happens is that we get a cluster state, in fact, a 6 cluster state after some time, and new links are introduced continuously, but it works. The goal function determines that we will finally end up in the 6 cluster state, and the speed gradient algorithm works by itself. We don't have to externally impose anything. And finally, this system shows the 6-cluster synchronization. It takes a little while. So I think I'll stop this here and just put on the conclusion. Well, general results, universal classification for large delay can be obtained with applications to neural networks and lasers. And we can also, by controlling the coupling phase, we can also stabilize different cluster synchronization states. And adaptive synchronization helps to self-adaptively find the appropriate coupling phase and also coupling strength, and even the network topology which supports such a synchronization. Finally, I would like to thank all my collaborators. There are many of them, some here, some elsewhere, and postdocs, also some of them are here, and my students. Thank you.
Thank you very much for this nice overview what can be done in general on delay coupled networks that for such a long time have been considered untractable or very hard to tackle. So we have time for questions, comments, ideas.
I'd like to imagine or assume you already identified the appropriate control parameter for your adaptive control. I wasn't really sure how in general you get to the appropriate goal function. I mean, do you have some kind of table for the different topologies and then just look it up, or?
That's a very good question, because there is no way of systematically constructing the goal function. So you have to rely on intuition and then see if it works. And a lot of these people in control theory use goal functions. They are convex, they have to be convex, and they have to be zero. So the most obvious one is paraboloid. That's what we've done here, but we've also used the Kuromoto order parameter. I mean, that's maybe less obvious, but it works. In fact, this is the one which we need to get the cluster synchronization. But there may be others. So no systematic way.
Other questions?
And the last part of control of the topology, you're always creating new links. Now, can you do the same, conserving the number of links?
That's also a very good question. We thought about that, but we haven't yet done it. But that's one thing we want to do in the future. So conserve the number of links and just adjust the strength of the different links. Here we have
or change the
or change links. Okay, that's another. That may be
more than changing the topology of the network. You are reinforcing the network with more and more links. Right?
Yes. However, we have to concentrate some conditions. So, for example, if we add a link, we have to decrease the force, the strength of the existing link to conserve the row sum. The row sum of all link probability is fixed. Let's say it's set to 1, equal to 1. So if we start with a unidirectional ring, this, let's say, has strength 1. Then we add these other links, and as you see, well, probably you don't see, but the original link becomes weaker. So the original link is weakened in order to conserve the row sum condition.
But it doesn't go to 0.
Not really, no. You see, this is...
You don't believe
yes, yes. This, it becomes smaller here, you can see, but it never goes to 0. But that's a vast field which need to be explored in the future. Do this with certain restrictions. Restrictions which might arise from real world, from experiments.
In the same context, maybe, the question. Certainly, the most powerful adaptive network is up here. So how far can one get inspiration from plasticity mechanisms in neural systems?
Of course, that was the idea behind, or one idea behind this work, because in the brain it's exactly what happens. By plasticity, you form or you weaken or strengthen links between neurons. And how can this be done self-adaptively in order to obtain a certain desired state?
Then you always have a function which certainly relies on local aspects like the spike time dependent plasticity, and then something which are more not really global but depend more on the environment, like intrinsic plasticity. So it looks like that a combination of both might be smart.
So this is certainly
from that aspect.
This is certainly just one aspect, but maybe one important aspect in the problem of how networks self-adjustively weaken or strengthen links in order to obtain a certain cluster synchronization state.
This seems to be quite relevant to the problem of cell differentiation. You know, this has been applied because cells differentiate, but not to any kind of tissue, but to very specific one. So there should be some adaptive synchronization that stabilizes cells to be just of, let's say, 10 or 12 different types, but no more.
That's another interesting problem which we haven't tackled. I mean, this is very new work, and I don't think other people have used that speed gradient algorithm either to optimize. But cells, networks of cells, genetic networks, cells, networks of cells, that sort of problem I think is very important, and I think it lends itself to applications, to future applications.
Maybe coming back to Ingo's question. So in the method that you use, can the links locally or are local informations enough for a link to change, or is there does each link have to know the state of the global system to adapt its own strength? So I mean,
well, in this is the equimotor order parameters modulus squared. So here and in this penalty term, the global properties come up. So the global properties do matter. And this is, this is a technical term which is really not essential. You can do it without this term, it works, but then the growth will not be 1, but some constant.
Probably you cannot avoid it because you want a certain global state.
Yes, I think you need to involve some global parameters, and this is the global parameter, the order parameter. I mean, this is the global parameter par excellence for this system.
I want to return back to the question Max and Ingo. Is there any theorem telling you how many links you have to touch to synchronize against it? I mean, here you have, if you are changing the values of J, which is an n times n matrix. There are 30 nodes, you have 450 values to touch. Probably you can synchronize an elephant with this.
We hope, yes, we hope to.
But the only thing you need to do is to move 2 n points in the complex plane, so 2 n variables, and you are using n squared numbers to do that. This doesn't look very good.
Yes. You have to.
Is there any threat to how many links? I would like to have not just all the nodes corrected, all with the others and with a real strength. I want to have only ones and zeros and see if it works, but I don't know if this is possible.
We have done this, but of course this is one thing we want to do to restrict the number of TI days. So far, what we can say is that this algorithm works rather efficiently independently of the initial conditions. Now, if you use initial conditions with different links set and different links maybe put 0, it still works rather robustly. So there is hope that we can eventually come up with algorithms which do not use n times n, but a much smaller number of links.
But this can be at the end, but I was just thinking of this moving the poles, the eigenvalues in the complex plane, looking at your picture that you said this is just a homework or a question for the questions. Why are some of the points outside of the
Yes.
Of the circle.
Yes. Well, that question is, I can simply answer that question. The master stability function, which is plotted here, does not involve the dynamic degrees of the links. And so we have an extended differential equation, and which has, of course, different stability properties. So that's why some of them are still outside the stable regime. But that's, I think, one approach is one really needs to understand how the final state, what characteristic properties the final states have, and what distinguishes them from other cluster states. And then, based on that, one could probably restrict the number of links and say, how can I move the eigenvalues in such a way that I get inside the stable regime?
In other contexts of dynamical networks and plasticity of networks, the relevant parameter is the ratio of two time scales. The time scale of evolution of the network and the time scale of evolution of the state of the node. And I couldn't see that sort of parameter coming here.
Yes, this is the time scale on which the network topology evolves. So it's, let's say, of order unity. And the internal dynamics is also of order unity. The time scale by which this involves is set by the gamma, by the relaxation constant of the speed gradient method. So if we set this time scale differently, we can make the time scales different, but then it takes longer for that picture. But for a realistic process in the brain, you have much larger time scale separation.
One more question.
Is this final state unique, considering different?
Yes. Yes. Mm-hmm. This is.
And the other question is if this algorithm or this adaptive system allows the appearance of self-feedback loops.
Yes, it does. This answer for the second question, yes, is allowed. And second, the first question, yes. This goal function has a unique minimum, and that's why we added this penalty. If we don't have this penalty, then you lose the uniqueness property, and then you can end up in different cluster states eventually.
So I think we can continue the discussion at our after colloquium break that kindly has been organized by Manuel again. So you're very welcome for some mimosa, for snacks and some drinks, and continue the discussion with Eckehard Schöll. He will also be here still tomorrow and Friday. So anyone who would like to talk to him and have some time to discuss, contact him directly, or Valentin, who is coordinating a bit his schedule. Thank you very much.
Very nice.
We have to discuss tomorrow by 10.
We have a meeting.